Okay, page 5. This should be a short lesson because we're just extending what we did yesterday with exponentials, but it's just not base E. So there's a little bit extra stuff that's going to come out of it, but it's going to feel like yesterday's rule. So we'll just go through a couple of examples. We may not finish this entire worksheet because I want to make sure I have some more time to do our test review for tomorrow, and then we can pick up anything we didn't finish up on Monday. So if you recall, derivative for e to the u is just e to the u times u prime. And anything that we're doing this semester, we're just undoing the process from first semester. So we know that, I mean, if e to the u is essentially e to the u, then the antiderivative is just going to be the same, right? That u prime is just kind of built into that du there. So if we're just going backwards, then e to the u must bring us back to e to the u. So we learned that e to the u is just e to the u plus c. And if those other base exponentials like 2 to the x, so examples of a to the u would be like 2 to the x or 3 to the x or 6 to the x. It's not base E. These are now base 2, base 3, base 6, but they all kind of fall under the same category that we call base A, just basically any base that's not base E. First semester, we learned that the derivative for a to the u looks a lot like e to the u. It is the original function, but then there's a conversion involving natural log that has to happen. So it needs to be natural log of a times a to the u times u prime. Now, this semester, we're going backwards. So imagine we're here on the right side trying to show that the antiderivative of a to the u is equal to basically a to the u. But this natural log of a has to go somewhere. We can't lose this. So it ends up having to be divided over to the other side. So a to the u's antiderivative would be this divided by this. So 1 over natural log of a times a to the u plus c. So it looks a lot like e to the u from yesterday. Exponential function is not going to change much, but there needs to be a conversion into base e. So there's this leftover coefficient that needs to be stuck with our answer. And then remember that natural log of a is just going to be some numbers. It's going to be some numeric coefficient that's going to hang out in front of my exponential function. So number one, our exponent is just x. There's no need for u substitution because it's just a singular x. So we can just follow the rule exactly as we see it. This falls under the category of exponential function, exponential base 2. So simply 1 over natural log of 2 times the original function. So the original function is it's going to appear in your antiderivative as well. Example 2 is also an exponential function. This time it's base 3, but looks like the exponent has a little bit more extra than just x, so we do need to go through u substitution. There is going to be something that's going to come out of that 4x. So we'll do u substitution. U equals 4x. Du dx equals 4. Cross multiply. We make our substitutions, replace the exponent with u, replace dx with du over 4. Now, one thing I want to make sure that we understand is that this 4 is not in the same category as this 3. We can't multiply these. We can't divide these. This is stuck as an exponential function. So this 3 is not a constant, even though it kind of looks like it. The 4 is a constant, but the 3 is part of an exponential function. So the 4 we can push out in front, but we can't merge the 3 and 4 together. So the 4 we can push out as 1/4. And now everything matches nicely with the rule that we want to use. So we start off with the coefficient. since that we definitely need to have that in place. And then we can move into the rule. So 1 over natural log of a, what's my a value here? 3, yep. So 1 over natural log of 3 times, and then a to the u, so the original function that you started with, 3 to the u plus c. And then your final step is to replace the u back in terms of x. Yeah. You can merge some things together if you like, but if you keep it all separate, there's no issues there either. Okay, let's just do one more because essentially, you're just doing u substitution and matching the rule, and then you're just plugging using the formula. Here, we have a base 5 function, 5 to the tangent of x. We can turn it into something that looks like a to the u. So our u value, again, is the exponent. And we're going to leave that secant squared alone in the hopes that it'll cancel out. Let's go through our steps, see if we can try this one. Here, the x's goes away. We need that to happen if we're doing the substitution, and there's no leftover coefficients. So we just have to worry about integral of 5 to the u. Okay, so we just follow what the rule says. We have a form of a to the u. My a is 5, so 1 over natural log of 5. That's just going to hang out in front. That's just going to be some coefficient that needs to be there because of conversion into base e. And then a to the u, 5 to the u, plus c. Replace the 5 in terms of, replace the u in terms of x. Yeah, so whenever you see a number raised to a variable, it's going to be a good fit usually for these exponential functions. Okay, these are just more complicated versions of our previous examples. So we can get to that on Monday as we get into our review. So there'll be a quiz next week. I may move it to next Thursday instead of Wednesday, but we're just going to review over what we did the last 3 days, where natural log, or just basically involving these rules here. And we'll go back and review these new trig rules 5 through 8. But we'll power rule. That's a carryover from before, and then our new ones: 1 over u, e to the u, and a to the u, plus these new trig rules. Okay. So I have a Riemann sums handout that we can go over. It says the rate of decay in grams per minute of a radioactive substance in a differentiable decreasing function R is given. The table shows decay rate if the substance has 3,000 grams to begin with, as recorded every 4 years over a 24-year period. So we have the amount in grams that the substance begins with, and then we have the rate of decay over the next 24 years in terms of the rate at which it's decaying. So part A, it says, using correct units, interpret the meaning of the depth interval from 0 to 12 of R of t dt in the context of this problem. Now, we know that there's going to be some transformation going on here, right? So if we're accumulating all these grams per year, what's going to happen if we were to take the integral of that? What are we going to accumulate, and what is our units going to be now? Will it stay as grams per year? It'll turn into what? That's what. So we talked about with integral here, think of it as you're multiplying these two units. So R of t is in terms of grams per year. But then you're accumulating that over a certain number of years. What's going to happen to my units? What's that going to turn into? Just what? Just grams. Right? So anytime you're doing an integral, you have to make sure that you're actually changing the unit. So whatever you start with, it's going to end up basically stripping away that denominator. Okay. But I think the struggle that a lot of students have is you see R of t and you feel like you have to hold on to that grams per year. But if you're accumulating that grams per year over a amount of time, your unit is going to change to the number of grams. So number of grams of radioactive substance that have decayed over the first 12 years. Whenever we find a derivative, we're changing the units. So the integral also changes our units as well. We're undoing our derivative back to the function level. Yeah, so whenever you see an integral, just think, okay, what's going to happen if my derivative changes back to my function? What's going to happen to my units? So if I have, so if I have any rate, my derivative is, that rate is going to turn back into just the numerator portion. Okay, next up. Using midpoint Riemann sums with 3 subintervals, approximate the depth integral from 0 to 24 of R of t dt. Show the computation that leads to your answer and then indicate the units of measure. Okay, so we already know that this is going to be in terms of grams. So we have all these accumulations of grams per year. And eventually, all that is going to accumulate to the number of grams. Then you hand down. So we're going to set up our midpoint Riemann sums. So we can set up our 3 subintervals. We have to extend from 0 to 24 with each subinterval spanning across the same number of order pairs. So then we can create one subinterval from 0 to 8, another subinterval from 8 to 16, and a third interval from 16 to 24. Subtract your t-values to get your width. It just so happens that the width here is all the same, but it doesn't have to be all the same. We have to just make sure and be comfortable with the idea that all these subintervals may be different. But we're just going through and finding area, right? So 8 times 95, because we're asking for midpoint. And then second rectangle is 8 times 80. Third rectangle is 8 times 65. So if we have this rate accumulated over the 24-year period, we're going to get the amount of substance that's actually going to accumulate too. So this tells us that over the 24-year period, 1,920 grams of radioactive substance will be decayed from that initial 3,000. So then part C is just asking us to determine how much radioactive substance is left, assuming that all this amount has decayed from that 3,000 to begin with. So 3,000 because that's the initial amount at the beginning of the problem. Yeah, so another thing so I want to keep reminding us, whenever you see an integral, just imagine that whatever you're looking at is referring to the derivative. And we know that the integral is going to transform a derivative up to the function. So if you transform a derivative to a function, your units will have to change from a derivative level to a function level. Right? Your rate is going to now turn into something at just the units level. All right, number 2. So here, the temperature of water in Mr. Brust's hot tub at time t is modeled by a strictly increasing twice differentiable function. So it's a smooth curve here. The temperature will keep rising in degrees Fahrenheit. Water is heated for 60 minutes, beginning at time t equals 0. Values of the temperature W of t is selected as select times are given in the table above. So part A, says use the data in the table to evaluate the definite integral from 10 to 30 of W prime. Now, if you look, we don't have W prime here. So this is not finding the area under this W of t because this is a different function here. But we can use first theorem to create something that is usable. If I take the antiderivative of W prime, what's that going to turn into? W prime is going to rise up to what level? W of t. And this is first theorem, right? This is basically f of b minus f of a. So we turn that W prime into its antiderivative, and then we plug in our upper and lower bounds. So W of 30 minus W of 10. So this is first theorem, right? First theorem says the integral from a to b of lowercase f transforms into uppercase f b minus uppercase f of a. So this transformation from lowercase to uppercase is this process from W prime to W. Now, what's W of 30 going to be? 85, right? W of 10 is going to be 63. Now, this is in terms of Fahrenheit here. So we get 22 degrees Fahrenheit. Now, what does this mean in the context of this problem here? The temperature is rising. You have W of 30 minus W of 10, 85 minus 63 equals 22 degrees. How can you describe what's happening here? What does that 22 degrees tell us about what's going on? If you know the temperature of the hot tub is 63 degrees at 10 minutes, and then if you know the temperature of the hot tub is 85 degrees at 30 minutes, what can you say? What does the 22 degrees mean? Would you say that the temperature of the hot tub is 22 degrees Fahrenheit? what does this 85 minus 63 tell us about what's going on? Good. So it tells us that between 10 and 30 minutes, the hot tub is going to rise 22 degrees. Right? It's the change in temperature over the 2 time periods. Yeah, so that's part B there. Using correct units, interpret the meaning. We know that the temperature of the water in the hot tub is rising, and over this 30-minute period, over this 20-minute period, temperature of the water will rise 22 degrees. Okay, so maybe you can use this 1 and 2 now that we've gone over it for you to practice on your own, 3 and 4. But I'd like for us to maybe do a full particle motion problem. I'm going to do this tomorrow morning as well, but I want to make sure that that we're comfortable with our calculator. And I'll leave all the top of the board there. I'll leave that up on the board in terms of those keystrokes on your calculator. So this is page 11 in your test review. Okay, object moves along a horizontal line, v of t. This is our kind of like our derivative graph here, velocity function. So in your calculator, you can type in your function under y1. Remember, you're only using x in your calculator. So x cosine of pi x over 6. Let me borrow a calculator. And then it says from 0 to 11. So you can go to window and then adjust your Ymin, Ymax. So I went from 0 to 11. That just tells me how far left and how far right I want my graph to go. And then I'm adjusting my Ymin, Ymax. You can kind of play around with it. You just want to be able to see the entirety of the graph. So usually negative 10 to 10 is a good spot for you to. So if you do zoom 6 will get you to your standard window. So yeah, you can type in zoom 6 as well. But it may show you more than you need to see because the interval is only from 0 to 11. So maybe I'll go, yeah, sorry, I should went back and do my X-Men. Let me see if this will be better if I change the screen. So X-min 0, X max 10, Y min negative 10, Y max 10. So hit graph. So this is basically my velocity or my derivative graph here. Let's create a sign line and just treat this like our derivative graph. So we know that we're looking for x-intercepts as our critical points. That's where velocity is 0. And if I want to find these critical points, we can use a certain feature here. You do second trace 0. And then you're just going to scroll to a point to the left of your x-intercept, hit enter. Scroll to a point to the right of the x-intercept, hit enter again. And then it'll say guess question mark. And then you can hit enter a third time, and the calculator will zero in on that x-intercept for you. In this case, it ends up giving you 3. So there's a x-intercept at 3. Next up, I would like to find this other x-intercept here. So again, do second trace 0. So I have that up there on the board to find x-intercept, second trace 0. We're trying to make the calculator find it for us. So we're just picking 2 points on either side of our target, and the calculator will look for that target for us. So left bound. So I'm picking a point to the left of the x-intercept, hit enter. Then it's asking me for right bound. So I'm going to go to the other side of the x-intercept, hit enter again, and then hit enter a third time. Now the calculator knows it wants me to look for an x-intercept between those 2 indicated points. I get 9. Now, if you see this number like 9e to the negative 13, that's just basically a number really close to 0. So just understand that's basically a y equals 0. So y equals 9, x equals 9. Okay, remember you're looking at the derivative graph here. So above the x-axis is positive, below is negative. In other words, positive velocity above and negative velocity below. Right, acceleration. Think of acceleration as looking at your derivative graph, trying to find your points of inflection. And you know your points of inflection are the peaks and valleys of your max and mins of your derivative graph. So if I want to find the max of my graph, I'm also going to go to second trace. But you see how I'm not looking for an x-intercept anymore. I'm looking for a relative max. So you're going to click on the maximum. So the calculator is now going to ask for a left bound. So you're going to scroll your cursor to the point, because ultimately you're trying to find this point, but you're going to make the calculator do it for you. So you're going to pick a point to the left of their relative max. And then hit enter, it's going to ask you for right bound. Then he's going to scroll to a point on the other side of the max, hit enter again. And now the calculator, hit yes question mark, the calculator is going to actually look for that x-intercept for you. We're doing this last year. Okay. So left bound, I'll pick a point to the left of the x-intercept. Sorry, left of the max. And hit enter. And then to the right of my max, I'll hit enter again. Hit enter a third time. I get 1.643. And now I'll do the same thing again, but now with the relative minimum. So I'll do second trace minimum, and I'll pick points on either side, and it's going to find that minimum for me. Let me just jump to that number there, 6.542. And now you look at the slope, right? Positive slope on my velocity graph means positive acceleration. Negative slope on my acceleration, on my velocity means negative acceleration. And positive slope. Part B, find the times when the object is motionless. Well, motionless is whenever my velocity is 0, so my x-intercept. So 0, 3, and 9. Part C, find the velocity of the object at 4 seconds. So we're just going to plug 4 directly into our velocity function. You can do it manually, or you can make the calculator plug in for you. So if you do alpha trace 1, y1, and then just do parentheses 4, it's going to plug in that 4 into that velocity function that you have stored under y1. Units of measure is -2 inches per second. Part D is asking for the acceleration at 4 seconds. You know, acceleration is the derivative of velocity. So we're going to make the calculator find that acceleration value for us. So we do math 8. Math 8 will take you to your n derivative feature. D over dx. And then alpha trace y1. And then x equals 4. If you have an older calculator, if you do math 8, it's going to show you n deriv. So you're going to type in y1 under vars y vars function, and then comma x comma 4, and that will take you to the same number as well. And then to get to this x here, to get to this y1, you'll do vars y vars function y1. Part E, is the object speed increasing or decreasing? Well, we see that increasing, decreasing speed is referring to velocity and accelerations, comparing their signs. Because they have the same signs, we can say that speed is increasing. Now, something to make sure that you understand is make sure that you are referencing what you're talking about. So don't use the word they, don't just say the graph, don't just say same signs. Indicate what you're referring to. Say that the velocity and acceleration have the same signs at that time. Because on the AP exam, if you use they or it's or graph, the graders are not going to know which graph or which. So make sure that you're always naming whatever you're referring to. Part F, find the total displacement. Displacement is just the depth integral. So it's a depth integral from 0 to 11 of v of t. Now in your calculator, you're typing in y1, but y1 is not going to mean anything on paper. So make sure that you're calling it v of t. Or you type in the entire, or you write out the entire velocity function, but it's just easier to reference that v of t. So if you have y1 on paper, it is what the calculator is showing up, but that's just a random notation. It's not a notation that indicates displacement. So make sure that on the test that you're writing out integral of v of t. So you're going to do math 9. And then you just type in everything that you see, lower bound 0, upper bound 11, and then alpha trace y1 to get to your velocity function. And this tells us where the object is going to be between 0 and 11 seconds. 11 seconds is going to end up negative 10.9 inches to the left of where you started. Next up, total distance. Total distance is the definite integral from 0 to 11 of the absolute value of v of t dt. I'm looking for those notations as well as your answer. So you'll do math 9 first, then you'll do math number ABS to get your absolute value bars to show up. And then you're going to put in your velocity function, your y1, alpha trace y1. Okay, don't worry about H, I, or L. For J is finding a physical location at a specific moment in time. So we were using this formula, x of b is equal to x of a plus displacement. If I want to find out where the object ends up, I'm going to have to know where he begins and how much movement he makes. So if I want to find x of 11, if I want to find out where's the object located 11 seconds into its path or into its journey, we'll say x of 0 because that's the number the initial time value they give us, plus how much progress is made with displacement. So plug this in the calculator, but this is also a carryover from before, negative 10.9. So it's going to move 11 or 10.9 units to the left, starting at 3. So if he's sitting at 3 and he's moving left 11 units, it's going to end up negative 7.9. And last part here is just average value theorem. It's just the depth integral, but then we have that 1 over b minus a in front. So again, on the board there, there's going to be 3 FRQs tomorrow. There will be a derivative graph, like the ones that we've been working on the past couple of days. There'll be a particle motion problem like this. And there'll be a Riemann sums problem similar to page 7, but we also saw different variations of it with the new worksheet. Right, any questions? Tomorrow morning, 7:15, I'll work through some of the other problems in your packets. And then also answer any questions that you have. Oh, another formula that you want to make sure that you know is trapezoids. I'll send that out in the reminder. Not just area of a triangle. Well, obviously you can go area triangle, area of rectangle for Riemann sums, but then also trapezoid, 1/2 width, height 1 plus height 2. If I ask you for approximations using trapezoids, we need to make sure we have that. And I'll send out a reminder this afternoon. Bye, come get your phones. Also, I want to walk around to see if you have any questions, if you have any issues with your calculator, or if you have any questions about your calculator. Yeah, I'll keep it very top of the board. No, I think if I give it. Oh,
I think oh, okay, then good. I don't like it's all first.
Even for these. I know that they're supposed to be, but yeah, but it's, if there are no bound, there should be plus. But that's the. That's probably. That's fine. Yeah. And no.
Get that for you right there.
Yeah, this is asking for the derivative of this. So, in fact, it's under one.
So like they were totally right.
Both.
Totally right.
It's e raised to this.
Oh, so I don't give them the wrong part.
Got it. So it's 20 plus
I go back to the past the picture if I'm hitting.
e. So you want to use.
Is it should I come
No.
Oh, no.
Oh, that one is that. Use that one. E raised to the.
So I have to like shove it in there and like shove that. What is it?
Can I do that 8 off of that?
Okay, that's how we do, because they gave warnings, so it's like go, actually, no. But like people from a lot of ones, I really see the red ones. The sophomore center plays. I'm all for like. Okay, let me get.